Science Alliance side. Some of you know, if you're watching live, I've just been teaching all ages lesson on static electricity, which is why my hair looks like this. Hiya. So this is our second to last ever lesson of the IGCSE physics module that I've been teaching, but in September I'm just going to start them all round again because frankly it's been far too much work planning completely royalty free like online lessons to only teach them once. So it's the second to last lesson that I'm ever going to have to plan from scratch, hopefully, and then next year we'll start all over again. So we're doing astrophysics, and I said that we would do Redshift. So we've talked a little bit about something that is very similar to Redshift before when we talked about the Doppler effect. Do you remember the Doppler effect? When, say, an ambulance comes towards you, if you're stood on the street, it hurts and you should cover your ears, but if you don't do that, you might hear it go, Nina, 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 and the pitch of the note changes as it goes past you. It gets lower. Why? Well, it's because the pitch of a sound wave, I'm going to draw it on the board as it's not a sound wave, but this isn't a lesson on waves, so it doesn't matter, right? Pretend that this is a sound wave. However, the shorter the wavelength of a sound wave, the higher the pitch. So a sound wave where the waves all squish together like that will sound high, and a sound wave where the wavelength is stretched out like will sound low. And how it works is, I've got this gorgeous little royalty-free diagram of a train from Wikipedia to show you. Here's how it works, you see? The train on the left is staying still, it's given out sound waves, and they're all spreading out in the same direction, in like equal amounts on either side of it. Whereas when the train starts moving, obviously, as it moves, it's a little closer to the sound wave that it's just given off. So they get bunched up on one side, the sound appears to be higher to humans, and it gets lower on the other side. I was trying to think how I could show you this with if this was possible to do with a baking tray, like maybe next year in this lesson, I'll get you to bring a baking tray of water. You see, if I put my finger in the middle, the waves just spread out in all directions the same, but if I move my finger, do they bunch up? I'm not sure you can see that, but kind of. Anyway, that's called the Doppler effect, where these waves seem to get squished or stretched out. The Doppler effect happens to things that are in space, right? Like in air, for example. But a very similar thing can happen with light. Let's get all my coloured pens out. So if you saw the wave lessons, we have talked before about how all the different colours of light have got slightly different wavelengths. Red has got the longest wavelength, and well, it's purple actually. It's got the highest wavelength, the shortest wavelength, and then green, just because I want to use more pens, will be somewhere in the middle. So, what redshift is, right, is we've looked at the light coming from distant stars and galaxies, and we've noticed that the light coming to us from different stars and galaxies is a little bit more stretched than we would expect it to be. So, say a star is giving off all the different colours of the rainbow, the whole spectrum, red, orange, yellow, green, blue, indigo, violet, it's giving off them all. Whatever particles are kind of in front of the star, they will absorb certain bits of the spectrum. They'll absorb certain colours of light. And what we've noticed is what we call these absorption lines in the rainbow are in slightly different places how I would expect them to be. I'll show you this handy diagram from, I think, NASA. Love NASA. So this might be what we would expect our star to be giving off. This rainbow of colours, but there's little black lines where, for example, like hydrogen is absorbing that certain colour of the rainbow, right? Or whatever particle it is, helium or something. This is what we'd expect, this one on the top, and this bottom one is what we would actually see. You can see the absorption lines are just a bit shifted towards the red end. It doesn't mean that the light that we're seeing from the distant galaxy is necessarily red, but just a bit closer to the red end than it would normally be. And we call this light sort of being more stretched than we were expecting it to be. We call that redshift. So for the rest of this lesson, I'm going to kind of be talking like redshift and the Doppler effect are the same. They're technically not the same, but at this level, you kind of say that they're the same. The Doppler effect is something, as I say, moving through space, whereas redshift is caused by space itself expanding. More of that this lesson and more next lesson as well. Right, if you've got a balloon, bring the balloon with you to this lesson. It's too late if you're watching, you didn't do it. Here's a balloon. Can you get a pen and just put some little dots on a balloon. This is an excellent model for how this works, because it's a weird idea. Like, what scientists have noticed is that everywhere we look, all the galaxies, so we talked a few weeks ago about how we live in the Milky Way galaxy, this huge cluster of billions of stars, but there are loads of other galaxies around us. Whatever galaxy we look at, we find that all the light from those galaxies is slightly more shifted towards the red end. It's like the light waves are getting stretched. So I've already done this, sorry, so I can't do it with you. Get a balloon and put dots all over it with a pen. Can you do that, please? So what would be the conclusion from that? If you think about what we said about the ambulance, where the waves get squished and then the waves get stretched, you see all light is being stretched and you think, well, maybe all the galaxies are moving away from us. And that's kind of true. So if everywhere we look, all the galaxies are moving away from us, you could conclude from that, well, Earth must be at the centre of the galaxy, right? Earth must be at the centre of the whole universe and everything else is spreading out from there. That is not the case, and this is a very good way of showing how that is not the case. If you've put dots all over your balloon, take a nice deep breath from down here and blow up your balloon and imagine that all these dots are galaxies, including our galaxy. So the Earth is in one of these dots as well. Do you see how all the dots have moved away from each other? It's not that there's one dot in the middle that they're expanding out of. What all this redshift around us is suggesting actually is that the universe is expanding. But we will do more about that next week. Landed back on the table. So, we've been talking about how there's two different exam boards that write your IGCSE physics paper. You can study what edXL want you to learn and they'll have a certain stuff on the exam paper, or you can study what Cambridge want you to learn and they will have a slightly different exam paper. For almost the whole of this course, thank goodness for us, they've wanted you to know pretty much the same thing. So I've just been teaching the lessons pretty much for both, maybe saying, oh, Cambridge need you to know this little extra thing. It's just edXL that needs you to know this equation, but I certainly think it'll help if you're doing Cambridge as well to know this. But when you learn about Redshift, you might get, especially on the edXL paper, if you're doing that one, you might get a question that involves this equation. I'm laughing, it's a really scary and strange looking equation. So my job as a physics teacher is sadly not to just show you this equation and then plug numbers in. I have to show you where this equation comes from, and that is what I'm going to, kind of what I'm going to do. It's not going to be quite right what I show you. I'm going to sort of pretend that redshift and Doppler shift are the same because I think it's all right for this level and I think it will help you understand. But know that what I'm going to tell you, not actually quite... Here's the equation, right? The equation for redshift. This is what we need to learn about today. I'm excited. Change in wavelength divided by reference wavelength equals velocity of a galaxy, like speed of a galaxy, divided by the speed of light. And another way of saying that in symbols is this little symbol lambda, which means wavelength, minus lambda 0 divided by lambda 0 equals delta lambda, like change in lambda divided by... It all looks very confusing, so I'm going to talk you through how this works. Okay, are you ready? So, you remember wavelength from yonks ago, our lessons about waves? If you don't remember wavelength, it doesn't matter. Here it is on the board for you. This is a wave. And the wavelength, it's a distance, okay? It's measured in meters, just like distance is measured mostly in physics. So wavelength is just the distance between the start of one wave, the start of the next wave. It's like the length of one wave, if you like. And there's an equation that we can put wavelength into. So you've probably heard of the equation, speed equals distance divided by time. Yeah, speed equals distance divided by time. Not a complicated equation. So if wavelength is a distance, okay, then we can say that the speed of a wave is distance divided by time. And we can say, all right, instead of just writing distance, we'll write wavelength. So the speed of a wave is equal to the wavelength of the wave divided by time, okay? However long it took for that wave to travel that distance. Okay? You with me so far? Wavelength is a distance, speed equals distance divided by time, so the speed of a wave equals its wavelength divided by a certain time. Cool. Right. Found the cutest picture of the sun and earth I could to help us with this. So here is the sun, And here is light travelling from the sun to Earth, as it does. Let's just make that one wavelength, okay? We'll go up and down and then up again. So that's just one wavelength, just to make it simpler. But we'll make it a little bit bigger. That wavelength, we'll say, is lambda 0. That means the original wavelength, just the normal bog standard wavelength that you would expect the sun to be giving off. If the sun or whatever star we're talking about wasn't moving, then the original wavelength given off by the star would travel towards Earth, and then we would be like, okay, that's the wavelength, cool. That is not what's happening, because as we've discussed, everything's moving away from each other, so that star is moving away like this. Behold my amazing special effect. Pew! So what does that mean? Well, we've talked about it. It means that this wave kind of gets stretched, right? As the sun is giving off this wavelength, it's also moving, so that wave gets stretched. I've shown it here in red. And that's the wave that ends up traveling to Earth. And that's the one that we end up observing and studying. And we're going to call that just wavelength we observe. It just gets the symbol lambda, like wavelength. Means wavelength that we observe. I know it's deeply confusing because this looks like the wavelength original looks like wavelength O, which could mean is the wavelength we observe, but it's not. Wavelength O is the original wavelength, the one that the sun would have given off if it wasn't moving, if everything was just straightforward. And this wavelength we observe is the one that's been slightly stretched. Okay. By the way, there's a YouTube channel called like Physics with Keith or something, where a guy called Keith describes like all the stuff that you need to know for GCSE. And I was delighted when I watched his derivation, which is very different to mine, that he was also saying things like, oh, I'm really sorry about this. Is this even helping? I don't even know if this is helping. So Keith, thanks. I didn't really use any of your work, but you sure did make me feel better about how hard I'm finding this as well, if you're watching. Right, you can look Keith up later if you don't approve of what I'm doing here. So, what wavelengths have we got? We've got this original wavelength, okay, which is the one just given off by the sun if it wasn't moving, what we would expect to see. And we've got this wavelength that we actually observe because it's the stretched one that comes to Earth. There's something else on here that we haven't labelled that astronomers are really interested in as well, that crops up in that equation that I just showed you. Any ideas what it is? I could give you clues, but I'm not gonna. Not yet. We've got the original wavelength. We've got the wavelength that we observe. Anything else you think it would be sensible to label that we haven't labelled that might help us when we come to measuring these waves and working out what's going on? I was getting some excellent answers on Facebook. None of them were right, but they were all showing excellent thinking. What astronomers want to know is the difference between them. So the longer wavelength, take away the original wavelength, the difference, there is. And we call that, if you're familiar with this, this little triangle means delta, it means change in. So that's change in wavelength, and that's the difference between the one that we've actually seen and the one that actually sort of you would expect to be given off. Okay, right. Because what does the difference between them tell us? More of that later. Oh, a cliffhanger. Okay, here's that equation again. So hopefully some of these are starting to sort of, even if you can't quite remember what they are, they're starting to look a little bit less terrifying. The wavelength that we observe minus the original wavelength divided by the original wavelength equals the change in the wavelength. Hopefully this bit is quite easy, right? I just showed you that the wavelength that gets to Earth minus the wavelength you were expecting, that equals the change in the wavelength. Yeah, so that is just another way of writing that. There you go. Long one minus a short one equals the difference. The velocity of a galaxy, well, I've been talking about stars, but I'll just show you my face for a bit. Hello. But if you're looking at different distant galaxies, it's quite hard to just pinpoint the light coming from one individual star in that galaxy. So quite often astronomers will just sort of look at all the light coming from the whole galaxy, because that's like an average of all the light being given off by all the stars, right? So we can talk about the light from a star being redshifted, but we can also talk about the light from a galaxy being redshifted. So let's replace a cute little picture of the sun with a cute little picture of a galaxy instead. There we go. And I'll try and talk about galaxies from now on. Right, so we've got these two different waves, original wavelength, what the wave sort of should be if the star or the galaxy was moving, and we've got the difference in the wavelength. So a little reminder, whoops, that the speed of a wave is equal to just distance divided by time, or the wavelength divided by the time it took for that wave to travel. So let's put some equations onto these wavelengths then, all right? The speed of this wave, the speed of the wave that the galaxy sort of has given off, or would have expected to give off if it wasn't moving. Well, it's travelling through space where there are no particles, this little wave that's just been given off by this galaxy, right? This light wave, if you like. It could be anything, couldn't it? It could be X-rays, whatever. But this light wave here, what's its speed? What is its speed? It's travelling through space where there are no particles. It's the speed of light, isn't it? It's travelling at the speed of light because it is light. And astronomers, physicists, call the speed of light little c. So instead of saying the speed of the wave equals wavelength divided by time, can we start saying the speed of the wave is the speed of light? So we'll replace that with a c. And the wavelength, well, we're talking about this original wavelength here. So let's change that equation. So it's the speed of light equals the original wavelength divided by a certain time. Is that all right? We've just come up with an equation to tell us what the speed of this wave is, the wave that would have been given off by the galaxy if the galaxy had not been moving, the original wavelength. Okay, let's come up with a little equation for this stretched wave then, or rather the change in wavelength here, this little bit here. An equation for the change in wavelength, well, what speed can we use for that one? Well, the galaxy is moving, right? So we can use the speed that the galaxy is travelling away from us. So it's not necessarily travelling at the speed of light. We'll call that speed v. That is the velocity of the galaxy. Do you remember this? This came up right in that equation. So we're looking for an equation that tells us, that sort of uses this wavelength and speed. We're going to use this wavelength, this little change here. I keep saying wavelength. It's a change in wavelength. The speed of the galaxy moving away from us, and we'll put that into this speed equals distance divided by time equation. So we've got v, the speed that the galaxy is moving away, equals the change in wavelength, the kind of extra bit of wavelength, divided by time. Right? Okay. I should say, it doesn't matter 100% if you're not completely following this. You won't ever have to do this in an exam. It's just very good practice for a physics teacher to try and give you a vague idea of where these equations come from. So we've got two equations. Look, behold, if you're into maths, oh, I've moved it back too far. If you're into maths, you might be getting quite excited now about the fact that we've got two equations and they've both got time in them. They've both got the same thing. What can you do if you get two equations and they've both got the same thing in? Here's what we can do. I'll put up here, this is what your spec says, what the specification says. So this is the equation that we're trying to make sense of. We've got two equations, v equals delta lambda changing wavelength divided by time, and the speed of light equals the original wavelength divided by time. We've got time twice. So let's rearrange them so they both say time equals. We've got time equals changing wavelength divided by the speed that the galaxy is travelling away. And we've got time equals the original wavelength divided by the speed of light. Is that okay? I've just rearranged those equations so they both say time equals. Now what can we do? Well, if time equals that and time also equals that, they must all equal each other, right? So we can just get rid of the times and just put those two things together. Now, this is where I, as your physics teacher who stopped physics teaching to have children 8 years ago, started freaking out because I suddenly thought, oh my days, are those times the same? Are those times the same? If that time and that time are the same, then we can say that all those things are equal to each other. And then I thought, if those times aren't the same, I'm going to be so annoyed because I just spent all this time doing a PowerPoint. Are those times the same? Let's think about it. It's the time that it took for the galaxy to move that distance, and it's the time that it took for that wave to travel that distance. And I thought, yeah, they are the same, aren't they? Those times are the same, obviously, because it gave off that wave while it was moving. So it's just all in that one period of time. Again, it doesn't matter if you're not following. I just thought it'd be interesting to feel what was happening in my slightly rusty, panicked teacher brain. So we can put those things together. So now look, we've got changing wavelength divided by v equals the original wavelength divided by c. This is all starting to look very familiar, isn't it? We just need to do a little bit of rearranging. Hopefully you can do that now at this level. We're dividing by v on this side. So let's times by v on the other side. And then we're timesing by the original wavelength on this side. So let's divide it on the other side. Yay! We got there. Whoop, whoop. Phew. Okay. So now I've done my job as a teacher. Finally, we can just start plugging numbers in and see if we can just do things with this equation. Here we are. What is redshift, by the way? I was going to ask you, but I've already accidentally put it on the screen. You might think redshift is just how much the light is stretched. You might think that redshift would just be that change in wavelength, but it's not. It's the change in wavelength divided by the original wavelength. Is the redshift bit of that equation. And astronomers call the redshift Z. So this is the equation that you need to know. And but it's the change in lambda divided by lambda 0, which is the redshift. Do you get it? So you can call that whole thing Z, that's redshift. So another way of saying this equation would be the redshift, how much the light is stretched, equals how fast the galaxy is travelling away divided by the speed of light. Please, let's just put some numbers in. Phew, finally, there we go. Right, so that's your redshift bit of the equation. We'll start out by just trying to find some redshifts. An absorption line A, shown on this little diagram here. I've just said that this is absorption line A, and as you can see, this is where we were expecting A to be, but when we actually measured it coming from a distant star, it was shifted over to the red end of the spectrum. So we were expecting it to have a wavelength of 432 nanometers, but it's actually observed at a wavelength of 454 nanometers. What is its redshift? And if you like, Lara, too easy. Okay, also, what is the unit for redshift? Whoa. So here's your redshift bit of the equation. The change in the wavelength divided by the original wavelength. This is quite hard. Have I given you enough information? You need the change in the wavelength. So you need to get these two wavelengths and minus one away from each other to get the change, the difference between them. And remember, the original wavelength is the one that you were expecting. I'm going to do it on the board while you're hopefully doing it as well, and then show you my answer. This was supposed to be a kind of practice one, so I'll try and go through this reasonably quickly, and then I've got another one for you to do on your own. Be so careful about what numbers you use here, haven't you? It's really easy to go wrong in exams here. Okay, like I say, I've got another question which is identical to this one but with different numbers. So if you haven't finished, don't worry, I'll talk you through this one and then you can do the next one on your own. Right, what is the redshift? How much has this shifted towards the red? Well, the equation for redshift is just change in wavelength divided by the original wavelength. So first thing you need to do is find the change in the wavelength. So the observed wavelength is 454 nanometers, but you're expecting it to be 432. So you've just got to do 454 minus 432 to get your change in lambda, your change in wavelength. So the change in wavelength is 22 nanometers, okay? So you know that is 22 nanometers. So you need to go, okay, change in wavelength, 22 nanometers divided by the original wavelength. This is where it gets tricky. It's the original wavelength that was given off, the one you're expecting. So it's 432 is the number that you use. So the answer is 22 nanometers divided by 432 nanometers gives you, divided by 432 equals, you should have 0.05, and what's the unit of redshift? Great question for you. People were struggling. Even the people who are normally quite cocky on Facebook were struggling with this, which is always nice to see as a teacher. What are the units for redshift? What's nanometers divided by nanometers? Well, what's 3 divided by 3? Or 6 divided by 6? Or a billion divided by a billion? Or a squillion? Is that number? I don't know. They cancel out. So there aren't any units to Redshift. Ah, surprise! Yeah, there's no units to Redshift. That's good, isn't it? After all this time, me shouting at you to put the units in, you don't have to put any units in. I know. Right, you ready for some more questions? See how you get on by yourselves now. Here we go. Question number 1, which is exactly the same as the last question you just did, but with different numbers to give you a bit more practice. An absorption line, A, is expected to appear on the spectrum of star at a wavelength of 420 nanometers, is actually observed at a wavelength of 450 nanometers. What is its redshift? Question number 2. Oxygen has an unshifted wavelength of 500.9 nanometers. If it is observed in a galaxy's spectrum with a wavelength of 596.1 nanometers, what is the redshift of the galaxy? And a galaxy has a redshift of 2. At what velocity does the galaxy appear to be moving away from Earth? If a galaxy has a redshift of 2, at what velocity does the galaxy appear to be moving away from Earth? And I've got U equation up here. So it's changing wavelength divided by the original wavelength is the redshift, but all that equals the velocity of the galaxy V divided by the speed of light C. Okay, I'm going to do it behind you one at a time. I am writing down all my working as well, and even putting in the units, because you never know when they might give you something that isn't in nanometers, and then you need to make sure that you haven't got caught out. Okay, I'll go through the first 2 answers with you, and then I'll do the last one. So the first one, an absorption line is expected to appear on the spectrum of a star at 420 nanometers, but it's observed at 450 nanometers. What is its redshift? So again, the first thing you need to do is find the change in wavelength. So we're going to do 450 nanometers, take away 420 nanometers, which gives you 30 nanometers. And then you need to divide it by like the original wavelength, the one that you're expecting. So you divide it by 420 nanometers. So 30 nanometers is your change in, and then your redshift is your change in divided by original, which I got to be 0.07. Did you remember to not put any units in? It's so weird, isn't it? Someone was on Facebook was saying, oh, well, could you write Z to show that it was redshift? And I said, no, you couldn't do that, because in algebra, that's like 0.07 times redshift, isn't it? Which is a totally different answer. If you're sort of worried that you might forget, you could say like equals Z. That would be fine to show that equals the redshift. And the second one, oxygen has an unshifted wavelength of 500.9 nanometers, so that's wavelength 0. If it is observed in a galaxy spectrum with a wavelength of 596.1 nanometers, what is the redshift of the galaxy? So you've got to find the change in, which is 596.1 minus 500.9, which gives you 95.2 nanometers. And so then again, the redshift is that divided by the original wavelength, which is the unshifted wavelength. So the answer was 0.19. It's so weird, not having units. Okay, I'm going to put equals Z. That makes me feel a bit better. And this last one, I've given you a slightly surprising result. And the very last one, a galaxy has a redshift of 2. What velocity does a galaxy appear to be moving away from Earth? Well, you don't need to worry about this equation now, the change in wavelength, because they've just given you that. So it's 2 equals the velocity of the galaxy divided by the speed of light. So you just rearrange that equation, don't you? And so, yeah, I've put here kind of redshift equals 2. Therefore, 2 equals V divided by C. Therefore, if you're dividing on that side, you times on that side. So V equals 2C, which is twice the speed of light. Whew! So more of this next week, more of how that is a thing. Okay, a few little cool facts about, oh, that's me. A few little cool facts about redshift before we go, and why blue shift is kind of a thing as well. The more redshifted a galaxy is, the faster it is moving away from us. Are you okay with that? The more stretched the light is, the faster it must have been moving. Hopefully that kind of makes sense. If you picture an ambulance, the faster it goes away from you, the longer the sound wave would be, so the lower it would sound, right? The faster the redshift, the things moving away from us, the bigger the redshift. And it turns out that the further away a galaxy is, the more it is redshifted. This was an astonishing realisation that we made. It's only quite recently that we've been able to measure the light from distant galaxies. The furthest away galaxies are the most redshifted. What? We're doing this a lot more next week, but the conclusion to this is the further away a galaxy is, the faster it appears to be moving away from us. Which, like I say, brings us to the Hubble constant, which we will talk a lot more about next week. And then I've just written blue shift on the board to remind myself to mention it. Blue shift is a thing. I must admit, I can't quite tell from reading the specification whether it would ever come up on your exam, but it's not that difficult to understand, luckily. So just very quickly before we go, don't know if you know this, most stars are actually binary stars. It's very, very common for a star to not be one star at all, but to be 2 stars which are orbiting around each other. So if you imagine that I've got 2 stars here, imagine that this one's kind of coming out of the board and then back in, and that one's going into the board and then back out again. Everything is moving away from each other. More of this next week, because Big Bang. Space is expanding, but if say my head is Earth, if you were observing these stars, at some point, this star here, from this angle, because they're rotating around each other, it would be coming out of the board, wouldn't it? So it would actually be coming towards me. So that's the situation where light would appear a little bluer, more violet, but bluer than you were expecting. So that wave would be slightly squished, which is when blue shift happens. It doesn't mean that the universe isn't expanding. It's just, yeah, a kind of sort of little local effect like that if something happens to be moving towards you while it's moving away from you. Yeah, so that's blue shift. I'm not sure whether it would come up, but yeah, with blue shift, the number for the redshift would be negative because the difference is smaller because it's getting squished, right? So you're doing like a smaller number divided by, you get it? Is that right? So the difference would be a minus number. So you could call a blue shift a negative redshift. Slightly confusing note to end the lesson on. There you go. That is the end of the lesson. Thank you so much for joining me. Oh no! I hate it when that happens. Very rarely does this happen now. I thought I'd posted on Facebook saying that this lesson was happening, and what happens was I posted on Facebook saying this lesson was happening, and Facebook went, oh, hold on, just before we publish your post, are you hosting an event? No, I just wanted you to post the original post, but it's too late now. Oh, sorry. So this is me now posting the post that I thought I'd already posted on my Facebook page that I hadn't posted. Wow, live Facebook posting via YouTube, fun times. So, well, I won't hang around and see if anyone is going to go to my Facebook page to comment. But if you're on YouTube and you're watching live now and you want to leave me a comment on Facebook, that is now there. Sorry. So you can. You couldn't have done until now, but you can now. Yes, right. I can't believe it. Can't believe that next week is potentially, I know they're going to end up changing all the specifications and I'm going to have to plan a load more lessons from scratch, but next week I will have taught the entire IGCSE physics syllabus, more or less, online using only copyright-free materials. And it's taken 2 years and I'm absolutely shattered, frankly. Blooming heck. But the really nice thing about it, the thing about this lessons, which doesn't happen with the all ages lessons that I teach, is that because it's an exam course, it does just repeat and repeat and repeat. So in September, I'm going to start all over again, but I'm going to already have the lessons that I made a bit of a hash of the first time round so that I can improve them. So if you are joining me not right at the end, if you didn't start from the beginning, that's quite good for you, because they're all hopefully going to be a little bit better and a little bit better after this point. So next week's our last lesson on cosmology, where we learn about the Big Bang. And then in September, I'm just going to start all over again with like electricity and forces and waves. It's nice. I mean, it was 2 years ago, so I know of quite a few people who've come to all of these ones. They're just going to start all over again, because free, innit? So you can watch as many as you like before you decide you want to do the exam. Oh, Isaac, yay! Hello! Spiders versus scorpions. That's a good one, because they're both arachnids. That's a really good one. Spiders v scorpions, yeah. Because we've done spiders, but we've never done a show about... I don't think we've ever done a show about scorpions. All right, that's on the board. Thanks, Isaac. Thanks for leaving me a comment as well. Thanks for making that my my Facebook post was not in vain. Okay, lovely people. If you want to pay me for these lessons, by all means, please do. Someone has to, or I cannot make a living. Actually can't. Whole family relying on this income now due to unfortunate circumstances beyond our control. So if you want to support me, you can go to my About section on YouTube, or you can go to my sign up button on Facebook. It takes you to this website called Coffee, or you could just write Coffee Theatre of Science into the big time now, that it will take you to the right place. And basically, yeah, you sign up to support me with £5 a month, which hopefully, for everything that I'm doing, isn't too much from you, but it all adds up for me to make this a job. And I will send you nice things to say thank you. I will send you Theatre of Science magazine, which is definitely suitable for all ages, because I am a qualified science teacher and I very rarely know any of the information that goes into the Theatre of Science magazine before I start researching it. So if you haven't got this magazine, you can support me with £5 a month and I will send it to you. This one's massive because it took me ages to get it just the way I wanted it to get. So my supporters had to wait for a long time. So I made it extra big because I felt guilty. So it's got Choose Your Own Adventure in it, about acids. It's all about acids. I send you some acidic sweets so that you can taste something acidic. I don't think it's got anything that anyone's allergic to in it. I did my best to find those. And you can read about why acidic foods taste sour. There's a which acidic object are you quiz, because you guys love those. There's a beautiful comic about acid rain, quite in-depth article, comic about what is acid rain, how did we discover it, how things got better. There are some beautiful activities you can do involving acids. Very proud of Data Science Magazine. So thank you to everyone who gets it. This is literally down to you that I can do this because you're getting Data Science Magazine. All right, I'm gonna go have some honey and lemon and make the printouts for this lesson that didn't materialise in time for the lesson. I'm really sorry. And do your homework PDF. Start planning for next week, the last week. Thank you so much for coming, and I'll see you all soon.